Welcome to the deep dive. If you've been following AI at all, especially generative AI, it feels like information overload, right?
Oh, absolutely. Every day there's something new.
Exactly. Stunning images, text, code. It seems like magic. But what's really going on underneath? And maybe more importantly, how are people actually building these things?
That's the million-dollar question.
So today, we're diving deep into generative AI, how it actually creates all this cool new stuff. And we'll look at the tools developers are using, especially a framework called LangChain.
Right. And our goal here is really to cut through that noise for you. We want to give you those aha moments, a clear, structured way to understand this stuff, from the basic AI types all the way to how developers actually build and deploy these applications.
And we've pulled this from a bunch of sources, overviews of Gen AI, NLP, prompt engineering guides, deep dives into LangChain itself.
Yeah, a good mix. We're looking at the what, but also the why it matters.
Okay, let's start right at the beginning then. AI, artificial intelligence. How does it even learn?
Well, at its heart, AI is about machines simulating human intelligence, And they learn from data, lots and lots of data, through a process called training.
Training, okay. And our sources highlight two main ways AI operates, discriminative and generative. This seems pretty fundamental. Can you break down that difference for us?
Definitely. Think of discriminative AI first. It's like a super efficient sorter or categorizer.
Okay.
You train it on labeled data, say, pictures clearly marked as cat or dog. Then you show it a new picture and it predicts cat or dog. It discriminates between classes.
So good for classification tasks, like spam filters.
Exactly. Perfect example. Is this email spam or not spam? That's a discriminative task. Or asking, is this picture a nest or an egg? It gives you a label. But crucially, it can't really understand deeper context, and it absolutely cannot generate a new picture of a cat or a nest.
Right. It only sorts what it's shown.
Precisely. Now, generative AI, that's the artist, the creator, it learns the underlying patterns and structure of the data it's trained on.
The patterns, okay.
And then you give it a prompt, could be text, an image, whatever, and it generates something entirely new based on those learned patterns. It's mimicking creativity.
So instead of, is this a nest, you'd say?
You'd say, draw me a picture of a nest with 3 blue eggs in it. And it creates that image. That's the generative magic. It's imagining, not just categorizing.
That distinction is super helpful. And both of these often use deep learning, right? What makes it deep?
Deep learning. It's about using artificial neural networks with many layers. Think of it like this. The first layer might recognize simple edges in an image.
Okay.
The next layer combines those edges into basic shapes. The layer after that might combine shapes into objects, like eyes or a nose.
Then eventually, a face.
Exactly. It learns features at different levels of abstraction, getting deeper and deeper. That hierarchical structure is what makes it deep and so powerful.
Got it. So that's the foundation. Now let's get into the specific engines that make generative AI tick. We're talking GANs, VAEs, transformers, diffusion models. It's amazing how this field evolved, right? Roots in the 50s, big jumps in the 90s and 2010s.
And then GANs in 2014 really shook things up.
Yeah. Let's start there. Generative adversarial networks, GANs. What's the core idea?
Competition. Pure and simple. You have 2 neural networks working against each other. One's the generator. Think of it as a forger.
Okay, a forger.
Its job is to create fake data, like a fake image that looks totally real. The other network is the discriminator, the detective.
Trying to catch the forger.
Exactly. The discriminator's job is to look at an image and say, real or fake. They train together. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting the fakes.
So they push each other to improve.
Constantly. Until the generator makes fakes so good, the discriminator's basically just guessing. It's like a counterfeiter and an expert detective locked in an arms race.
Great analogy. And we see this used for realistic faces, art styles.
Yep. Creating those hyper-realistic faces you sometimes see, or mimicking artistic styles, that's often GANs at work.
Okay, next up, VAEs. Variational autoencoders. How do they fit in? Are they competing too?
No competition here. It's a different approach.
Yeah.
VAEs are about learning a compressed, sort of meaningful representation of data, like learning the essence of something.
The essence.
Yeah, and then using that essence to generate new, similar data. The key difference from a standard autoencoder is that VAEs are probabilistic.
Probabilistic meaning?
Meaning instead of just compressing data to one specific point, they learn a distribution like a fuzzy cloud of possibilities for each input. To generate something new, they sample a point from that cloud and reconstruct it.
Ah, so that fuzziness allows for variation.
Exactly. It learns the range of what a smile could look like, not just specific smiles it's seen. So it can generate brand new, plausible smiles, used for faces, handwriting variations, morphing images, that kind of thing.
Okay, that makes sense. Now, transformers. You mentioned they're huge for language models. What's their secret sauce?
Transformers really changed the game for sequential data, like text. Their core trick is attention, specifically self-attention.
Attention, yeah.
Simplified, for every word in a sentence, the model looks at all the other words and figures out how relevant they are to understanding that specific word.
So it's weighing importance.
Right, like in "the dog ate the food because it was hungry," attention helps the model figure out that it refers to the dog, not the food.
Ah, I see. That's clever.
And the big advantage over older models, like RNNs, is that transformers can process all parts of the sequence at the same time, in parallel.
Faster then.
Much faster, and better at capturing long-distance relationships in text. It's like skimming the whole paragraph instantly to get the context, instead of reading word by word. That's why they power models like GPT and Gemini, and are great for translation, code generation.
Makes sense why they're so foundational now. Okay, last one in this group. Diffusion models. These seem to be behind those amazing image generators lately.
They really are state-of-the-art for image quality, often. The core idea is, well, it's kind of backwards. Yeah, they learn to generate data by starting with pure random noise, like TV static, and then progressively removing that noise step by step until a clear image emerges.
So they learn how to denoise.
Exactly. They're trained by taking clear images, gradually adding noise until it's just static, and learning how to reverse that process perfectly. To generate, you just give it noise and let it run the reversal.
Wow. Like sculpting from a block of static instead of clay.
That's a great way to put it. And the results are incredibly high quality, very diverse, often better realism than GANs, and generally more stable to train. Think DALL-E 2, stable diffusion, that's diffusion models at work. Also used for editing, audio, video.
Incredible. So these powerful models, GANs, VAEs, transformers, diffusion, they form the engine. Now, our sources talk about foundation models. How do they connect to generative AI? Why are they such a big deal?
Foundation models, a term from Stanford, are a really important concept. They're AI models trained on absolutely massive amounts of broad, unstructured data, usually in an unsupervised way.
Unsupervised, like just learning patterns?
Yeah, like learning to predict the next word in a sentence. The quick brown fox jumps over the lazy. It learns to predict dog. Because they're trained on so much diverse data, they develop really broad capabilities.
But they're not specialized for one task.
Exactly. That's the key. Unlike old-school AI built for one specific thing, foundation models are highly transferable. You can adapt them to many different tasks. And yes, they are definitely part of generative AI because their core function is often generating something, the next word, an image, code.
That transferability sounds powerful. Does it mean we just prompt them, or can you actually tune them for specific jobs?
Both. You can tune them. You take a pre-trained foundation model and fine-tune it on a smaller, specific data set for a task like sentiment classification. You update its parameters a bit with labeled examples.
Okay.
But what's also amazing is how well they work with just prompting, especially in context learning. You give them model instructions and maybe a few examples right there in the prompt, and it figures out the task on the fly.
Without retraining.
Without retraining. Like, you could prompt it, review, this movie was terrible, sentiment, negative review, love the acting, sentiment, positive review, it was okay, I guess, sentiment, and it will likely answer neutral.
Wow. Okay, you mentioned NLP earlier, natural language processing. Let's circle back to that. What is it and why is it so critical for AI talking to us?
NLP is basically about giving computers the ability to understand human language, spoken or written, and derive meaning from it, just like we do.
So, bridging the gap between how we talk and how computers process data.
Exactly. We talk in unstructured ways. Hey, add milk and eggs to the shopping list. Computers prefer structured data, like a neat list, shopping list.item, eggs, item, milk. NLP provides the tools to translate between those. NLU, natural language understanding, is the input part, and NLG, natural language generation, is the output.
Where do we bump into NLP every day?
All over. Machine translation, obviously. Trying to keep the meaning right, avoiding the vodka's good, but the meat is rotten kind of errors.
Right, the classic translation fails.
Yeah. Virtual assistants like Siri and Alexa use NLP for speech. Chatbots use it for text. Sentiment analysis on reviews, spam filters, analyzing email text. It's everywhere.
How does it actually work under the hood? What tools does it use?
It's like a toolbox. First, you need to break the text down. That's tokenization, splitting add eggs and milk into tokens like add eggs and milk.
Okay, individual words or pieces.
Right. Then you might want the root form of words. Stemming is a crude way, just chopping off ends, running, runs, ran might all become run. But it's not always smart. Yeah, university might become universe, which isn't helpful. Lemmatization is smarter. It uses a dictionary to find the actual base form, the lemma, so better becomes good.
Much more meaningful.
Definitely. Then there's part of speech, POS, tagging, figuring out if make is a verb or a noun in context, and named entity recognition, NER, identifying Arizona as a state, Ralph as a person, Google as an organization.
So it's all about adding structure and meaning to raw text.
Precisely. Transforming our messy human language into something structured that AI can work with effectively.
Okay, so we have these powerful models, and NLP helps them understand us, but how do we guide them? That brings us back to prompts and prompt engineering. What makes a good prompt?
A prompt is basically your instruction to the LLM. It usually has two key parts: the clear instruction telling the AI what to do, and the necessary context, background info, data, details it needs to do it well.
So it's more than just asking a question.
It can be, yeah. A simple prompt like "the wind is" might get a poetic answer, but for specific tasks, you need more structure.
Which is where prompt engineering comes in.
Yeah.
Why is this skill suddenly so important?
Because the way you ask the question dramatically affects the answer you get from these powerful LLMs. Prompt engineering is the craft of designing those prompts, instructions, questions, context in the best possible way to get accurate, relevant results.
So it's about maximizing the LLM's effectiveness.
Exactly. Better prompts mean better accuracy, more relevance. It helps meet user expectations, reduces weird misunderstandings. And crucially, good prompting often means you don't need to constantly fine-tune the model. You guide it using the prompt itself.
How do you structure a prompt effectively then? What are the components?
A really well-structured prompt often includes 1, the instruction, summarize this article; 2, context, this is for a busy executive who needs the key points; 3, the input data, the article text itself; and 4, sometimes an output indicator, summary.
That makes sense. Clear roles for each part. Now, what about in-context learning again, and those shots, 0, 1, few shot prompting?
Right. In-context learning, ICL, is a key prompt engineering technique. You give the LLM examples of the task right in the prompt. It learns from those examples during inference without needing retraining.
Super efficient.
Very. Though it's limited by how much text you can fit in the prompt. Now the shots. 0 shot means no examples given, just the instruction. Translate this sentence to French. Relies purely on the LLM's pre-existing knowledge.
Okay.
1 shot gives 1 example. English? Hello? French? Bonjour. English. Goodbye, French.
Guiding it with a single case.
Yep. And few shot gives a few examples. Maybe 3 to 5 examples of sentiment classification before asking it to classify a new review. Helps it generalize better from a small set of demonstrations.
Are there even more advanced techniques for complex reasoning?
Oh, yeah. Chain of thought, compu-prompting is a big one. You explicitly ask the LLM to think step by step or show its reasoning.
Like showing your work in math class.
Exactly like that. It forces the model to break down complex problems like word problems or logic puzzles into intermediate steps, which usually leads to a much more accurate final answer.
Makes sense.
And then there's self-consistency. This is clever. You ask the model the same question multiple times, maybe with slightly different phrasing, or asking for different reasoning paths.
Generating multiple answers.
Right. You generate several independent answers and reasoning chains. Then you look for the most consistent answer among them. It's like getting a second, third, and fourth opinion from the AI to boost confidence in the result.
That's smart. Kind of like crowdsourcing from the AI itself.
Well, you could think of it that way, yeah. Very effective for complex reasoning tasks where one path might go wrong.
Okay, so we know how to talk to these models. Now, for developers wanting to build applications using LLMs, things get complex fast. This is where LangChain comes in, right? What is it exactly?
LangChain is essentially a framework. It's open source, mostly Python, designed to make building LLM-powered applications much, much easier.
Easier how?
It provides building blocks, standard interfaces, and ways to connect components together. It helps you manage prompts, connect to different LLMs, retrieve data from external sources, process information, and chain all these steps together into a coherent application.
So it handles the orchestration.
Exactly. That's a great word for it. The chain in LangChain literally refers to chaining together operations. Maybe retrieve some data, use an LLM to summarize it, then use another LLM call to format the output.
What are the big advantages for a developer using LangChain?
Several big ones. Modularity is key. You can swap components in and out easily, like Lego blocks. Extensibility, it's designed to be customized and integrated with other tools. Decomposition, it helps break down complex tasks into smaller logical steps, which often leads to better results. And it makes integrating with things like vector databases much simpler, which is crucial for searching large amounts of information semantically.
Where are people actually using LangChain? What kind of apps?
All sorts. Summarizing long documents like legal contracts or research papers, extracting specific data points from text, building sophisticated question-answering systems that can pull information from multiple documents or databases.
Like smarter chatbots?
Yeah, much smarter, context-aware chatbots. Also, automated content generation, drafting emails, brainstorming ideas, writing code documentation, lots of use cases.
Is it just for text? Or can it handle images, audio?
Primarily text-focused, but it's designed to be flexible. You can integrate it with other libraries to handle multimodal data. For instance, use a speech-to-text library to process audio, then feed the text into LangChain. Or use models that generate image embeddings, store those in a vector database LangChain can access, and do semantic search over images.
Okay, let's peek inside LangChain. What are some of the core components developers work with?
Well, first you have the language model itself, the LLM or chat model. LangChain provides standard ways to interact with models from OpenAI, Google, IBM, Hugging Face, etc.
So you plug in your chosen model.
Right. Then you have chat messages. These structure the conversation. Each message has content, but also a role. Human message, a message, system message. The system message is important. It sets the context or persona for the AI, like, you are a helpful assistant.
Got it. Structuring the dialogue.
Exactly. Then prompt templates are huge. They help you dynamically create the prompts you send to the LLM, inserting user input or context as needed. There are different types for simple strings, chat conversations, few-shot examples.
Making prompts reusable and dynamic.
Precisely. And related to few-shot prompts, there are example selectors that help pick the best examples to include in the prompt, maybe based on semantic similarity to the current query.
What?
Finally, output parsers. These take the raw text output from the LLM and transform it into a more useful, structured format, maybe JSON, a list, a CSV, whatever your application needs downstream.
Okay, so components for input, prompts, messages, the core model, and output parsers. Makes sense. Now the chaining part. What are LangChain chains?
Chains are the core concept. It's simply a sequence of components linked together, where the output of one step feeds directly into the input of the next.
It's like an assembly line for processing information.
Exactly. A common type is a sequential chain. Imagine wanting to find a country's famous dish, then its recipe, then cooking time. Chain 1 takes China, outputs Peking duck. Chain 2 takes Peking duck, outputs its recipe. Chain 3 takes the recipe, outputs cooking time.
A multi-step workflow.
Right. LangChain makes setting up these kinds of sequential and other types of workflows much easier.
For these chains, especially chat applications, memory seems vital. How does LangChain handle remembering the conversation?
Memory is crucial, you're right. LangChain has built-in memory components. Their job is to store the history of the interaction, the human messages, the AI messages.
So the AI doesn't forget what was just said.
Exactly. Before a chain runs, it can read from the memory to get context. After it runs, it writes the latest turn of the conversation back into memory. This allows for stateful conversations that feel much more natural.
Okay, chain sequence calls. But then there are agents. How are they different? They sound more autonomous.
They are, in a sense. An agent in LangChain uses an LLM not just to generate text, but as a reasoning engine to decide what actions to take and in what order.
So the LLM is planning the steps.
Yes. Instead of a fixed chain, the agent dynamically figures out the sequence. It has access to a set of tools, things like a web search, a calculator, a database query tool.
Tools for interacting with the outside world.
Right. So the user asks a question. The agent uses the LLM to decide, okay, based on this question, I should probably use the search tool. It runs the tool, gets result, observes it, and then the LLM decides the next step, maybe use the calculator tool on the search result, or maybe formulate the final answer for the user.
So it's more flexible, less predetermined than a chain.
Much more flexible. It can handle unexpected situations or queries that require accessing external real-time information or performing actions. You could build an agent that can query a database, analyze the data with Python, and then describe the results in natural language.
That's powerful. Now, there's this thing called LangChain Expression Language, or LCEL. Sources say it's the modern way to build. What's the deal with LCEL?
LCEL is a really elegant way to compose these chains and components in LangChain. It's declarative, meaning you define what you want the chain to do rather than explicitly coding every step.
Declarative, like SQL.
Kind of analogous, yeah. The core idea is using the pipe operator, the symbol, to connect components.
Right.
It makes the flow of data incredibly clear and readable.
Piping output from one thing to the input of the next.
Exactly. Prompt model output parser. It's clean, composable, and makes complex chains easier to understand and visualize. It also brings a lot of benefits under the hood.
Like what are the building blocks here?
The building blocks in LCL are called runnables. Pretty much everything, models, prompts, parsers, retrievers, your custom functions can be a runnable. You connect them with the piper. If you pipe runnables together, runnable 1, runnable 2, runnable 3, that creates a runnable sequence automatically. If you use a dictionary where values are runnables, like summary.model1, critique.model2, LCEL automatically creates a runnable parallel, running model 1 and model 2 concurrently with the same input.
Wow, concurrent runs just from a dictionary structure.
Yeah. And LCL automatically coerces things too. Pass a Python function. It becomes a runnable lambda. Pass a dictionary, runnable parallel. It's very intuitive.
So a simple example, maybe that joke chain.
Sure, you could have a prompt template, pipe it to your LLM, like Gemini, and pipe the LLM's output to a Stroutput parser to just get the final string. Prompt template, LM Stroutput parser, super clean.
That does sound much cleaner than defining sequential chains manually. What other advantages does LCEL bring?
Lots. Built-in support for parallel execution, asynchronous operations, async await, much easier streaming of responses so the user sees output incrementally, and automatic integration with tracing tools like LangSmith for debugging and observability. It's really the recommended way to build most chains now.
Okay, amazing tools, powerful models. Let's zoom out. For someone wanting to build a real generative AI application, what's the journey from idea to production?
It's definitely a journey. And increasingly important, Gartner predicts over 80% of enterprises will use Gen AI by 2026. So developers need these skills. The journey usually has 3 phases.
Phase 1.
Phase 1, ideation and experimentation. This is proof of concept time. You identify a specific use case, research models, Hugging Face, open source, vendor models, considering size, cost, performance, risks. Maybe start with prompting techniques, zero-shot, few-shot, chain of thought, just to see what's possible quickly. A key insight here is that sometimes smaller specialized models outperform huge ones for specific tasks, and self-hosting can be cheaper.
So experiment, find the right model task fit. Phase 2.
Phase 2, building the application. Now you're integrating things, maybe serving the model locally for privacy. Crucially, you're likely integrating external data. 2 big techniques here. RAG, retrieval augmented generation.
All right, pulling in external data on the fly.
Exactly, supplementing the LLM's knowledge. Or fine-tuning, where you actually modify the model's weights with your specific data to bake in domain knowledge or behavior. And you're heavily using frameworks like LangChain here to structure the application.
Makes sense. And phase 3. Getting it out there.
Phase 3, operationalization MLOps. This is about deployment, scaling, monitoring, using containers like Docker, orchestrators like Kubernetes, optimizing inference speed with runtimes like VLLM, often adopting a hybrid approach, maybe multiple models for different tasks, running some on-prem, some in the cloud, and then continuous monitoring, benchmarking, governance, updating data, prompts, testing new models. It's an ongoing cycle.
That ongoing cycle.
Yeah.
It sounds like managing these models is like gardening. Our sources use that analogy.
It's a fantastic analogy. You have to prepare the soil research the model's needs before deploying. You have to nurture its growth, constantly evaluate and optimize. You need a diverse garden, multiple models for different needs, making sure they work together.
And you need to weed. Ask tough questions.
Absolutely. Who built this model? What data? What risks? What guardrails? You define the use case, research, test, maybe start big, then try smaller. Evaluate, and then continuously monitor and govern. It needs constant care, and the whole team needs to be involved. Models evolve, the ecosystem evolves, so your strategy has to keep evolving too.
Great analogy. One last piece. Flask. It's a web framework. How does something like Flask fit into building these potentially massive Gen AI apps?
Flask is a lightweight Python web framework. It's a micro-framework, meaning it's simple to start with, but very extensible. For Gen AI apps, it's often used to build the API layer, the part that exposes the AI functionality to users or other services.
So serves up the AI.
Pretty much. While it's simple, you can scale Flask applications significantly with good architecture, modular design, caching, load balancing, etc. Its flexibility allows developers to quickly build and iterate on the API, while the underlying AI, maybe built with LangChain, does the heavy lifting. Major companies use it for APIs and backend services because it's flexible and performs well when scaled correctly. It lets you separate the AI logic from the web serving logic cleanly.
Wow, okay, we have really covered a ton of ground.
Hmm.
From the basic difference between generative and discriminative AI, through the core model types like transformers and diffusion models, into the nuances of prompt engineering, and then deep into building applications with LangChain, LCEL, and even deployment considerations with tools like Flask and that gardening analogy. It feels like we got that shortcut to understanding the landscape.
I hope so. The goal was to connect those dots from the fundamental concepts to the practical engineering. Understanding these pieces helps you see past the magic to the incredible amount of thought and work involved, and it's a field that's just moving so incredibly fast.
Absolutely. So for you listening, here's something to think about. As generative AI weaves itself more deeply into everything we do, how can you leverage these specific capabilities? Think about the creative power of diffusion models, the structured control of LangChain and LCEL. How could you combine these ideas not just to use AI, but to actively shape it, to create something new, solve a unique problem? What's the next thing you could build or imagine? This has been another deep dive. We hope you're leaving feeling more informed, maybe a little bit inspired about what's possible with generative AI.
Definitely. Keep exploring, keep questioning, and think about the amazing potential ahead.